Alright, so our goal with partial fraction decomposition is to take a fraction like this and turn it into smaller fractions that would have added together to get that in the first place. Here we go. Alright, let's do the partial. I'm going to do an example first and then I'll kind of give you some rules, okay? Let's do the partial fraction decomposition. That's too long of a phrase. Of 7x plus 1 over x squared plus x minus 6. Does that look familiar somehow? Okay, pretend it doesn't. Pretend this does not look familiar, that you do not know the fractions that add together to get this. Okay? All right, step 1, factor the denominator. Okay, so, what do we get? X plus 3, x minus 2? Right? Okay. Step 2. Write as separate fractions, each one with a factor from the denominator. Something like that, sort of. Just writing it in my own words. Okay, so we have two factors, so how many fractions are we going to create? Two fractions. So 7x plus 1 over x squared plus x minus 6 is going to be equal to something, we're going to call it a, over x plus 3 plus something, we're going to call it b, over x minus 2. Because then when we add these together, we have to get a common denominator, and this is the common denominator, so there will be something up there and something up there that eventually adds together to equal this. So right now these are variables that we don't know yet. Got it? Okay. Next. This is a problem to now solve that you should have learned how to do last year. But, of course, we're reviewing. So when you solve a problem, notice the equal sign in the middle. That means we're solving. When you solve a problem like this, you want to get rid of the fractions first by multiplying by the least common denominator. Okay? So the next step, step 3, multiply both sides by least common denominator. Okay, so what's the least common denominator? What's the least common denominator of the entire thing? Hello? It's this entire thing, right? X squared plus x minus 6. But the factored version would be easier. Anyway, I probably should have just rewritten this as the factored one, but it doesn't really matter. Okay, so I'm multiplying both sides by x plus 3 over x minus 2. And it's not even just a matter of multiplying both sides. It's like multiplying every fraction by that, just on the top. So it's just like you're multiplying that over 1. X minus 2. That should have been a minus, sorry. Over 1. Why is that legal to multiply that over 1 on everything? Because what you do to one side, as long as you do it to the other side in algebra, is a legal thing, right? Like taking the square root of both sides, or taking the log of both sides, or dividing both sides by a number, or multiplying both sides by a number. That's what we're doing. Okay? So then this entire denominator cancels with that entire thing, and we're just left with 7x plus 1. What cancels here? X plus 3's cancel, so we have a times x minus 2. What happens here? The x minus 2's cancel, so we have b times x plus 3. And we just got rid of the fractions entirely. But now we need to solve for a and b. Do we know what x is, and does it even matter what x is? It honestly does not matter what x is at this point, because the whole point of the problem to begin with is that it's a problem with a variable x, and so x is a variable, we don't care what it is, it can change, right? So, would it be okay for us to randomly choose x values that would allow us to solve for a and b? Because right now, don't we have 3 variables in this problem? We have variable x, variable a, variable b, and we want to solve for a and b. We don't care what x is because we're just leaving it as a variable. But we do want to know what a and b are, so we can know what the fractions are that add together to get this fraction. So is there a number we could choose for x that would conveniently get rid of x and get rid of either a or b? Because we can't solve for more than one variable at a time. 2. Alicia's thinking 2. Why, Alicia? If you plug a 2 into here, you get 2 minus 2, which is 0, and that cancels out a. Very well done. Okay, this is called the convenient x method of solving these. There is another way. Okay, so for your convenient x method, not math. Sorry. For your convenient x method, you plug in like x equals 2. Yeah, I'll leave that on the recording. Okay. So you let x equal something like 2 and you plug it in. So 7 times 2 plus 1 equals a times 2 minus 2 plus b times 2 plus 3. And then you simplify. So 7 times 2 is 14 plus 1 is 15. A times 0 is 0. And b times 5 is 5b. Now we simply solve for b. How do we do it? Divide by 5. So b equals 3. Right? That's one of the answers. Now what number do we need to find the answer to? Now we need to find a. So is there another number we could plug in to help us find a? Okay, so we could let x equal a negative 3. Here, I'm going to fold this so we can see everything better. Okay, so we're going to let x equal 3. So we have... If you plug in a negative 3 here, negative 3 plus 3 is 0. That causes b to go away so that we can solve for a. Okay, so 7 times negative 3 plus 1 equals a times negative 3 minus 2 plus b times negative 3 plus 3, sorry. So this would be negative 21 plus 1, so negative 20. And this would be a negative 5a plus 0. So then what does a equal? 4. A equals 4. Okay, so we just found b equals 3, and we found a equals 4. Are we done? No. We are sort of done. We just need to do the last step, which is going back to this piece right here and plugging in a and b. So our final answer will be 4 over x plus 3 plus 3 over x minus 2. And that is the partial fraction decomposition of that original problem, which we already confirmed at the beginning when I was showing you that we were going to go backwards. That's what we started with when we got this in the first place. So without even knowing that answer, we went backwards and found it.